Welcome back, everyone. So we're going to complete topic 2, finally, the slippery slope of life, with our final video. So we have basically we've come to the end of topic 2. So for now, you should know all the properties of life, what constitutes life, as well as describe the differences between prokaryotes and eukaryotes, and how they came to be, as well as the components of eukaryotic cells, as well as understand why viruses and prions are not considered cells, and the basics of chemistry. So how are covalent bonds, ionic bonds, and hydrogen bonds formed. So now we're going to finish off the chapter with the properties of water. So by the end of this video, you should be able to describe the properties of water that are critical to maintaining life. You should also be able to explain what pH is and the function of buffers. So first off, water is very important to life. So you might, think about when we're exploring the universe. It seems like, astrophysicists, they're always trying to see, they're always looking for if there's water on other planets out there, because that is an indicator that there's possibly life on those other planets. So water is essential to life. And the reason why it's essential is because, it's unique. So we're going to talk about why it's so, what are those properties that make it so unique? So one of the properties is that water is polar. Okay, so if we take a look at our kind of a refresher of our chemical bonds that we talked about in the last video, we learned about covalent bond and hydrogen bonds. Now, first off, we have to remember that a water molecule is made of covalent bonds. Okay, so this is a water molecule. So H2O, so two hydrogens bonded to an oxygen, and they are held together by covalent bonds. And remember, covalent bonds, they're strong bonds. Okay, so these are strong bonds. The hydrogens and the oxygens, they are held together with strong bonds, so they are not going to be breaking apart. And these bonds are formed by sharing of electrons. So they're sharing these electrons. It's a very strong bond. But as we remember, the sharing is unequal, and that's because of that unequal sharing of electrons, where the oxygen atom holds onto the electron from the hydrogen's shell a little bit more often than the hydrogen does. And so that makes it slightly more negative on this side of the water molecule and slightly more positive on this side. Okay? And because of that, you get this polar covalent bond. Okay, so that unequal sharing of electrons. And because of that, we end up with this slightly positive end. And this, we also have, between two water molecules, we can have a hydrogen bond. Okay, so a hydrogen bond can form between two water molecules. So remember, it's between two water molecules, it's not within a water molecule. So between two water molecules, a hydrogen bond can form, and hydrogen bonds are considered weak bonds. So it's just basically a slight attraction between the positive end of a nearby hydrogen with a negative end of a nearby oxygen. Okay, so they can have this attraction to each other that's kind of holds together and a temporary bond. All right. So that's basically that polarity. But remember, the water molecule itself is held together by a covalent bond. Okay, so just kind of remember that, because a lot of students, they get confused and they think that hydrogen bonds hold together the water molecule. Okay, so water molecule is held together by covalent bonds. water molecules, they have weak attractions to each other through hydrogen bonds, okay? So they're attracted to each other. Let's see, and then as far as other substances, when we have other substances that are polar, so other molecules that are polar, they can interact with water very easily. Okay, so if we have another substance that has this kind of configuration where we have slightly positive, slightly negative ends, then they might be attracted to water as well. So we might have a slightly positive end of another molecule over here that might be attracted to this water, this oxygen end of this water molecule. And when we see this happening, we call that substance hydrophilic. Okay, so hydrophilic is a polar substance that interacts readily with or even dissolves in water. So think of hydrophilic. Hydro means water, philic means liking or loving. I don't know what type of relationship. Do they like it or love it? So hydrophilic. Okay. The opposite of that would be hydrophobic. So hydrophobic means water fearing. And in this case, these are compounds or molecules that will not dissolve in water. And the substances that don't dissolve easily in water or bond with water are non-polar compounds. And if you think about it, a non-polar covalent bond, they are equally sharing the electrons. And since they're equally sharing the electrons, they're not going to be attracted to a negative or a positive end of a water molecule. So they're not going to, be interacting with the water molecule. They're not going to want to form hydrogen bonds with them. So they're going to be hydrophobic. Okay. So water's polarity is one of the properties of water. Okay. Another property of water is that water stabilizes temperature. Okay. So what is temperature? First off, temperature is a measure of motion. So when the temperature goes up, that means that the atoms or molecules, they will start moving around faster. Okay. When the temperature goes down, that means the water molecules or whatever we're talking about move slower. So when we think about this in water, when water is in liquid form, okay, so when they're in liquid form, the water molecules are forming hydrogen bonds and breaking hydrogen bonds with each other to form liquid water. When the temperature starts heating up, okay, that means that the water molecules are starting to move around faster. And as they are moving around faster, they're moving away from each other. And so they're breaking those hydrogen bonds. And as they're breaking those hydrogen bonds, they're moving away from each other and they start evaporating. So evaporation occurs when more bonds between the water molecules are broken than are formed. And so that results in a release of individual water molecules from the surface of a liquid. Okay. And then the opposite occurs when the temperature goes down. So as the temperature goes down, the motion of the water molecules slows down. And as it slows down, the hydrogen bonds start to, stay in place. Okay, and so if they're staying in place, they actually end up forming this lattice structure. So I'm just going to kind of show you that, what it looks like in a 3D form. So this is this lattice structure of a bunch of water molecules. So you can see the individual water molecules, but you can see how they're held together in like this. It's a crystal shape, okay? So these are solid water, okay, so in the form of ice. And in between, look, there's space. And this indicates that when water freezes, it becomes less dense or more spread out than liquid water. Okay? So that explains why frozen water or ice floats. Okay, so liquid water is more dense than solid water. And that explains why ice floats and water is, below it. Okay, and that helps a lot because if we have a lake and it freezes over, it's going to be freezing from the top going down instead of from the bottom going up. So if you're a fish in the lake, it's going to be a lot easier for you to survive if it's freezing from the top going down. If it's going from the bottom up, there's nowhere for you to go. Okay, so this is basically how water stabilizes the temperature. Okay. So it creates that. So basically that ice will form on that surface. Also, because it's forming on the surface, it creates like an insulating barrier to protect everything below it. So it prevents the water below it from freezing. Okay. Another property of water is that it is an excellent solvent. So if you remember, water is polar, and because it's polar, a lot of things are attracted to it. Other polar things are attracted to it. Because it's polar, it has slightly positive or slightly negative charges. And so other things are capable of dissolving in the water. So water is a solvent that can dissolve solutes, okay, the things that are dissolved within the solvent to make a solution. So for example, we have NaCl. So remember in our last video, we talked about NaCl. So sodium basically had an extra electron in its outermost shell, so it wanted to lose that electron to form a cation, and chlorine wanted to gain that electron to form an anion, and so they formed an ionic bond. And as doing so, that ionic bond made them form a molecule or a compound called salt. So when you put salt in water, what happens? Well, it dissolves. And what's happening as it dissolves is that the water molecules, the ends of the water molecules, the slightly positive ends and the slightly negative ends, will be attracted to the anion and the cation of the salt compound. So for example, we have the anion, okay, so the negatively charged ion here, the chlorine. The hydrogen ends of the water molecule are going to be attracted to it, and the chlorine, it being negative, is going to be attracted to the hydrogens. And so the hydrogen ends of the water molecule are going to surround it. And so now it's completely surrounded, and it's completely dissolved. It's broken apart from the sodium. Same with the sodium, okay? The sodium is a cation. It has a positive charge. So the oxygen ends of the water molecule are going to be attracted to it. And so eventually it's going to be surrounded by the oxygen ends of the water molecule. So it's separated. And so now the salt is completely dissolved in the water. It's mixed in. Okay, so that means that the solvent has dissolved the solute in the solution. Okay. Another property of water is that water is cohesive. So what is cohesion? So cohesive or cohesion basically means that water molecules, since they are polar in nature, they're going to be attracted to each other, okay? They're going to cling to each other. So cohesion means like clinging to each other. So intermolecular forces between water molecules. So they're clinging to each other. They hold on to each other. So think about if you have like if you just washed your car or your car was rained on and you see little water droplets form. So those water droplets form, they're kind of clinging to each other to form that little water droplet. And that's due to cohesion. So instead of the water spreading out, it's held together into like a little droplet. And so that's due to the cohesive forces, due to the polarity of water. So water is cohesive. It clings to each other. This also explains surface tension. So surface tension is where we have tension at the surface of a body of liquid that prevents molecules from separating it. So if you've ever seen, you go to a pond or a stream and you might see like those water striders, those insects that kind of can walk on water. So they can do that due to surface tension. So they are able to just barely touch the surface of the water, and due to surface tension, due to the cohesive forces of water, they are able to sit on the surface of the water and not break the surface. Okay? Or if you're very, very careful, you can try this experiment at home where you take some water and then just carefully see if you can set a needle on top. And the surface tension of the water should keep the needle suspended. Okay, so it's just light enough that the weight of the needle should basically be just enough that it won't pull it down into the water. Okay. So cohesion is when we have water molecules, they kind of stick together. Adhesion is an attraction or sticking between water molecules and other molecules. Okay, so think of if you have a straw and you're sucking up liquid through the straw. Okay, and then when you're done, there's still a little bit of liquid stuck to the straw. So that's adhesion. Okay, so when the water is sticking to the side, that's adhesion. So it's adhering to the side. So the water is clinging or adhering to other molecules to the side of the straw. So this is important when we're talking about, do I have it on the other side? I don't. Talking about something called capillary action. So if you think about trees, where do plants get their water from? They get it from their roots. But trees are huge. And water needs to travel all the way from the roots all the way up to the top of the tree. And so it does so through this, basically it's a vascular system called xylem, which are these tubes. And it does this due to water can go against gravity up the roots of the plant all the way to the top of the tree due to adhesion and cohesion. Okay, so the water can cling to the sides of the xylem, and the water can cling to itself to basically go against gravity to get pulled up to the top of the tree. So that's due to adhesion and cohesion. Okay. All right, and then finally we get to pH and buffers and acids and bases. So first off, we're going to talk about, well, first of all, we should probably talk about pH. So pH is just a solution that measures, it measures acidity or alkalinity. But well, what's an acid? What's alkaline or a base? So an acid is a molecule that donates hydrogen ions. And so it's going to increase the amount of hydrogen ions in a solution. So hydrogen ions is basically just H+. So if a solution has a lot of H pluses in the solution, then it's acidic. Okay. A base is the opposite. So a base donates hydroxide ions. Hydroxide ions, you notice, are negative. So what happens is when we add a bunch of hydroxide ions into a solution, they bind with the excess hydrogen ions, and so that decreases the amount of hydrogen ions in the solution. And so there's going to be less amount of hydrogen ions in the solution. So that would be more basic. So that means when we look at a pH scale, we're actually looking at the concentration of hydrogen ions in the solution. So the higher the concentration of hydrogen ions, the lower the pH. The lower the concentration ions in the solution, the higher the pH. So think of it as an inverse scale. So basically, if for right in the middle, we have an equal concentration of hydrogen ions to hydroxyl ions. Okay, so it's about equal, and we call that neutral. If we have a lower concentration of hydrogen ions to hydroxyl ions, we call that basic. If we have a higher concentration of hydrogen ions to hydroxyl, we call that acidic. And so you can kind of see some of the everyday products of where they land on the scale. Okay, so neutral right in the middle would just be like distilled water. And a lot of stuff that is related to the human body usually falls right around there. So like our blood pH is 7.35 to 7.45, so it's just slightly alkaline. Our urine is right about 6, okay, so it's a little bit more on the acidic side. Inside our stomach, our stomach is breaking down our food products, so that's actually very acidic. Okay, down to 1. And that makes sense because we need to break it down into smaller parts. Okay, and then you kind of see some other stuff. So bleach is on the opposite side of the scale, so that's it's very alkaline. Baking soda is pretty alkaline. Orange juice, lemon juice, tomato juice, they're all pretty acidic. And then finally we get to buffers. So buffers are substances that they actually resist changes in pH, and they do so by either absorbing hydrogen or hydroxyl ions, or they release hydrogen or hydroxyl ions into the solution. So by doing so, they prevent the solution from becoming more acidic or basic. So it keeps the solution's pH the same. So for example, here we have something that happens in our body. So in our body, as I said before, our body's, our blood pH is right about 7.35 to 7.45, slightly alkaline. And in order to prevent our blood from becoming too acidic or too alkaline, it has a buffering system. So this buffering system basically involves carbonic acid. So carbonic acid being this H2CO3, as well as bicarbonate. So bicarbonate is this HCO3 negative. So you can see this would be an example of an anion. So if we end up with too much hydrogen ions entering the body, then the bicarbonate will combine with it to form carbonic acid. And that will limit the pH from becoming too acidic. Okay. Or if we have too much of the hydroxide ion introduced into the system, the carbonic acid could then rapidly dissociate into bicarbonate and hydrogen ions, and then those hydrogen ions can combine with the hydroxyl ions to form water, and that could limit the increase in pH. So the carbonic acid is very important in kind of preventing the fluctuations in pH. So it can either it could either dissociate and into bicarbonate and hydrogen ions, or the bicarbonate combined with hydroxy to form carbonic acid. Right? So this is an example of buffers. Now, buffers can be for any pH, okay? So it doesn't necessarily have to be, so this is keeping the blood pH around 7.35 to 7.4545. So it doesn't have to be neutral pH, it could be anything. So buffers can keep, any system, whatever the normal pH is for that particular system. All right, so let's do a review question. So which of the following statements is not true? Is it water is polar? Water stabilizes temperature? Water is essential for life? Or water is the most abundant molecule in the Earth's atmosphere? So which one of these is not true? If you said this last one, I would agree with you. Did we talk about it being the most abundant molecule in the Earth's atmosphere? No, we didn't. Okay, the most abundant molecule in Earth's atmosphere is actually nitrogen gas. So it is the most abundant molecule in your body, but it's not the most abundant molecule in our atmosphere. Okay, so that is not true. Water is polar, it does stabilize temperature, and it is essential for life, but it's not the most abundant molecule in our atmosphere. If it was, then our atmosphere would be very thick because there would be a lot of water in it. Here's another review question. Using a pH meter, you find the pH of an unknown solution to be 8.0. How would you describe this solution? Would it be weakly acidic, strongly acidic, weakly basic, or strongly basic? If you chose weakly basic, I would agree with you. Okay, so it's, it's past, it's not an acid because it's not less than 7 is an acid, but it's not a strong basic. Okay, so the pH scale goes from 0 to 14. So, it's just past 7, which is neutral, so it's a pretty weak basic. If it was closer to like 11, 12, 13, 14, it would be more strong. Okay, so weakly basic is the answer. And then finally, we have, we didn't really talk about this, so let's do it now. So the pH of lemon juice is 2.0, whereas tomato juice's pH is about 4.0. Approximately how much of an increase in hydrogen ion concentration is there between tomato juice and lemon juice? So when we were talking about the pH scale, we didn't talk about how it's a logarithmic scale. So as you go through the scale, in between the numbers, you're not increasing or decreasing the concentration of hydrogen ions by a factor of 1. You're increasing it by a factor of 10. Okay? So if I am looking at the concentration of hydrogen ions between distilled water and urine has 10 times more hydrogen than distilled water. Okay? If I'm looking at between urine and black coffee has 10 times more hydrogen ions than urine. If I'm comparing black coffee to distilled water, then I'm looking at 10 times 10 or 100 times more. Okay? Since we're going, twice here, so 10 to the second power. So every time you move up or down the scale by 1 point, you're increasing the concentration by, a power of 1. All right? So if I go from orange juice to seawater, okay? So I'm going by a factor of 1, 2, 3, 4, 5. Okay, so orange juice has 10 to the 5th power more hydrogen ions than seawater. Okay, seawater has, 10 to the 5th power less hydrogen ions than orange juice. So it's a factor of 10 for each individual spot. Okay? So with that understanding, let's see if we can get that question. So if the pH of lemon juice is 2, whereas tomato juice is 4, approximately how much of an increase in hydrogen ion concentration is there between tomato juice and lemon juice? So we go from 2 to 4. So there's a 3 in between. Okay, so that would be 10 times. That would be 10 times. So that would be basically your, 10 to the power 2, or 10 times 10, which would be 100. So 100 times. All right. So now we have completed the last section of topic 2. So what are the properties of water? So by now you should be able to describe the properties of water that are critical to maintaining life, as well as explain what pH is and the function of buffers. This also concludes our topic 2, slippery slope of life. So by now you should be completing all of your assignments, as well as taking the topic 2 quiz. So in the next unit, we're going to get into topic 3, which deals with the building blocks of life.